The river with the largest volume of water and with a length of 330 kilometers, the longest in Sri Lanka, is the Mahaweli. It is along this river that the largest present-day barrages are being built. Today's barrages are designed not only for irrigation purposes, but also for electricity generation and flood control. The largest of these reservoirs along the Mahaweli is the Randenigala reservoir. It is 12 kilometers long from the actual dam to the far end of the reservoir, has a water spread of 23 square kilometers and a capacity of 860 million cubic meters. This makes the Randenigala reservoir one of the largest in Sri Lanka. The construction work for the Randenigala hydroelectric power plant was executed by the joint venture Randenigala Civil Contractors, RCC for short. The partners in the joint venture were Dickerhoff and Widman, Bilfinger and Berger, and Alfred Kuntz, and Dickerhoff and Widman was the sponsor. The reservoir is situated roughly at the point where the Mahaweli River emerges from the mountains and enters the low-lying plains on the eastern side of Sri Lanka. There is a natural narrowing of the valley at this point, which meant that it was an obvious choice for this site of the dam. The name of the project was taken from Randenigala, the mountain which forms one side of this narrow section of the valley. Let us look at the main components of the hydroelectric power plant in turn. First of all, the actual dam, in this case an embankment dam filled with compacted rock. Even if the water reached its highest imaginable level, the reservoir should never overtop the crest of the dam, which means that a spillway is essential. This consists of a weir with chutes. The structures for electricity generation have been sited on the other side of the valley. The water flows through the intake tower into the penstock and then passes below one side of the dam to reach the powerhouse. After the head has been worked off, the water flows back into the river below the powerhouse. Work in the Randenigala Valley started with the halls were erected for the stores and workshops for the maintenance and repair of construction equipment. Then came a site power plant and facilities for providing and purifying drinking water and water for other uses. As soon as work on the site installations had progressed sufficiently to permit making a start on the first big construction operations, a bridge was constructed over the Mahaweli so that all the construction equipment could be transported to the site on the other bank regardless of the river's water level. The first step there was to build the site roads, an undertaking which in this steep, rough terrain was in parts like building proper mountain roads. One important requirement in running a large-scale overseas building site, in addition to properly functioning site installations, is ensuring that supplies of building materials run smoothly. Most of the other goods needed for the site, construction machinery, plant components, spare parts, small pieces of equipment, food, were transported directly to the site in their shipping containers. The cement imported for the Randenigala site was filled into big bags before it left the docks, and these were transported to the building site, 4 to 6 at a time, in normal lorries. In all, 92,000 metric tons of cement were used for the project. The Randenigala site is 230 kilometers from the port of Colombo, a whole day's journey by normal lorry. Now that supplies of materials has been ensured and the site installations completed, work could start on the actual hydroelectric power plant. The narrowness of the valley at the site of the dam meant that the Mahaweli had to be diverted underground while construction work was going on. This was achieved by building 2 parallel underground river diversion tunnels which were driven from the upstream end through the foot of Mount Randenigala. Each tunnel is 410 meters long with an internal diameter of 9.6 meters. To ensure good flow conditions, the tunnels were lined with reinforced concrete. As a preliminary to driving the tunnels, the building pit for the later intake structures was excavated. Once the excavations had reached a suitable depth, the first shot was performed on the first tunnel. As the rock around the face proved to have insufficient load-bearing capacity to guarantee that the tunnel would form a strong arch, the first few meters of the tunnel were provided with rock support, consisting of steel arches and wire mesh. A layer of shotcrete was then applied to seal the support with the rock and thus ensure adequate stability. The geological conditions around the face of the neighboring tunnel were more favorable. Here, the hydraulic drill carriage, the so-called jumbo, could be used right from the start. Tunnels of this diameter are normally mined in 3 sections. First, the top section, the crown, is excavated. Then comes the middle section, and finally, the floor of the tunnel, the invert. Once the entire tunnel had been excavated, work was started on constructing the inner lining of reinforced concrete, starting with the reinforcing and concreting of the floor of the tunnel. Although the project had already involved the use of several thousand cubic meters of concrete for the site installations, the camp, the bridge, and various other things, the concrete poured for the first tunnel floor was the first batch of a total of 200,000 cubic meters permanent structural concrete used for the Randenigala project. The production of the concrete was of crucial importance to construction operations. In the Randenigala area, there are no adequate supplies of natural sand and gravel suitable for making concrete. The aggregates for the concrete, therefore, had to be specially produced in a crushing and screening plant on the site. The rock excavated from the building pits and the tunnels was taken to this plant, where all the requisite grain sizes, ranging from sand to gravel, could be produced. The addition of cement and water and the mixing of the fresh concrete took place in a stationary, large-scale mixing plant. When placing concrete, particular attention must be paid to the temperature. Too high a temperature, combined with the heat subsequently generated by the concrete as it sets, can cause damage to the structure. In tropical countries, it is therefore especially important to ensure that the permissible maximum temperature for the fresh concrete is not exceeded. In Randenigala, no special measures were needed to cool the concrete during the cooler months of the rainy season, but during the summer, a whole range of measures had to be taken. The first step was spraying the aggregates with river water, that is, cooling by surface evaporation. A second step was the artificial cooling of the mixing water for the concrete, and a third step, which could be resorted to if necessary, was adding ice flakes to the freshly loaded transport vehicles. This meant that it was possible to adapt to the prevailing temperature and that the site could always be supplied with sufficiently cool, top-quality concrete. The reinforcement of the tunnel sections depended on the quality of the rock. In as far as reinforcement was necessary, reinforcing mats were mainly used. The formwork for the arch of the tunnel was erected with the aid of a steel formwork transport wagon mounted on rails. With this, the formwork for the entire arch, as from the upper edge of the floor, could be erected for one tunnel section at a time. As it did not take long to move the formwork wagon from one section to the next, it was possible to achieve high working speeds. In addition, the stiff, dimensionally stable steel design of the wagon made for very high dimensional accuracy, and the steel plate form lining meant that the surface of the concrete could be made extremely smooth. Once one section of tunnel had been reinforced, the formwork wagon was released from the concreted arch in its previous position and moved to a new section. The movable formwork elements around the wagon were hydraulically adapted to suit the geometric dimensions of the internal diameter and carefully adjusted. Then the ends of the tunnel lining were boarded up with individual planks and the concreting of the arch could begin. Openings were left in the form lining for introducing and compacting the concrete. The team of workers became so practiced at all these operations that they could concrete 12 meters of tunnel a day. Once the tunnels had been lined throughout, the two outlet structures were completed and the tunnels were ready for use. For the diversion of the river, a cofferdam was erected across the Mahaweli between the inlet to the two tunnels and the site of the dam. The river rose by a few meters and for the first time started to wend its way through the diversion tunnels. After the river had been diverted, a second cofferdam was erected across the Mahaweli just upstream of the outlet to the tunnels. The water left between the two cofferdams was then pumped off. This meant that the riverbed was now dry over the entire area where the dam was to be constructed, and work could now start on building the dam without being impeded by the river. The day for diverting the river had come. It was essential to ensure that the closing of the upstream cofferdam across the Mahaweli took place as quickly as possible, as the river constantly washed away part of the fill as it passed through the narrowing gap. However, the gap was closed and the river was cut off. The water rose very quickly and soon reached the protective dam, which had been erected in front of the intake structures for the diversion ceremony. This protective dam was now opened, and for the first time the river started to wend its way through the mountain. The old riverbed was now empty for the length of the diversion, and work could be started on the dam. It is very important that the surface of the tunnels should be particularly smooth in order to cope with flow spreads of up to 50 kilometers an hour. This rock-fill dam is 303 meters in cross-section at the base, and its crest is 485 meters long. The total volume of fill is 3.9 million cubic meters, with a maximum dam height of 102 meters. The cross-section of the dam shows how its impermeability and stability were achieved. In the center of the cross-section, there is an impermeable core consisting of fine-grained cohesive soil. To prevent particles of soil being washed out over this inner core over the years, both sides of the core are protected with a fine filter of sand and a coarse filter of sand and gravel. The two supporting shells of rock ensure that the combination of the core, the filters, and the supporting shells give the dam complete stability, so that it can be relied upon to deflect the horizontal water pressure down to the foundation. To protect the dam against damage by wave action, the top part of the upstream face and the bottom part of the downstream face are protected with specially chosen blocks of rock, which are put in place individually. Even before the river was diverted, work had started on removing all soil from the sides of the valley within the dam area until rock with a sufficiently high load-bearing capacity was exposed. Once diversion was complete, this work was continued on the floor of the valley and the riverbed. Another operation, which had begun long before the Mahaweli was diverted, was the driving of the grouting and inspection gallery underneath the dam. Not only does the dam itself have to be impermeable, but also the natural foundation below the base. To this end, and also for inspection purposes, a man-sized tunnel has been constructed along the entire length of the dam 15 meters below its base. From this tunnel, cement was injected into the underlying rock until it was grouted to a suitable depth. The impermeability of the grouted rock is constantly supervised by means of drainage wells. In view of the purpose to which it was to be put, checking impermeability and performing further grouting of the foundation if necessary, the cross-section of the grouting gallery could be kept relatively small. For this reason, it was not possible to use large machinery for mining it. Six months have now passed since the river was diverted. Along the length of the dam, at right angles to the dry riverbed, the enormous core trench has been excavated. This is necessary because the impermeable core has to reach right down to the solid, compact underlying rock. The trench has been excavated in steps at both ends so that the core embeds itself better in the sides of the valley. This is what the site looked like after excavation work had been completed and when the first filling operations for the core were just starting. The first work on the core also involves removing every bit of loose material from the surface of the rock in the trench area. Great care needs to be exercised here to prevent water from the reservoir later seeping into the joint between the inner core of the dam and the underlying rock. The cohesive sandy soil for the inner core was dug from a side valley of the Mahaweli about 3 kilometers away from the dam and could be used in the dam almost without any further treatment. The filter layers separating both sides of the inner core from the rock fill were produced in the site crushing and screening plant like the aggregates for the concrete. The rock for the dam's supporting shells was obtained from a newly opened quarry sited not far from the dam. Sometimes the blasted rock required dripping for loading. Generally, the blasting operation produced material of a size which could be used directly in the dam. This is the dam 18 months after the filling operations had started. The available working surface gets smaller and smaller as the dam gets higher, particularly as it is also shared with general site traffic. Layer by layer, the dam edges up to its final height, about 90 meters above the floor of the valley. The placing of the rocks on the slopes of the dam requires particular skill. In the course of time, the local excavator operators have got so familiar with their vehicle that they can move its arm almost as deftly as if it were their own. Now the dam has almost reached its final height. Work has also been going on around the clock on the spillway running along the side of the valley at one end of the dam. Spillways are constructed in order to channel off peak flows when reservoirs are full and to convey flood discharge to the bottom stream in a controlled manner without danger to the barrage. Normally, the 3 steel weir gates of the spillway are closed, but if the water level rises beyond a predetermined height, they're opened and the flood discharge is diverted down the chute and over the flip bucket, the maximum flow being 8,000 cubic meters per second. For the given head of 84 meters, the spillway must be approximately 300 meters in length. When the spillway is in operation, the flood water pounding down the chutes and flip bucket reaches flow velocities of up to 120 kilometers per hour, making it absolutely essential that the highest quality concrete be used for all the surfaces with which the water comes into contact. For this reason, a special procedure was used for the invert surfaces which were constructed without formwork. After the placement, spreading and compaction of the concrete, the fresh concrete was dehydrated with the help of vacuum matting. The water was then pumped off and carried away in pipes. The final task consisted in smoothing the surface of the concrete with mechanical floats. The piers are the load-bearing elements of the weir. They are 41 meters in height from top to foundation. The water pressure on the weir gates, amounting to a maximum of 1,900 tons per opening, is transmitted to the weir piers via pre-pressed anchors. Dividag strand tendons, which had been pre-stressed with the help of big pre-stressing jacks, were used for this purpose. The weir is opened and closed by means of 3 steel segment gates, each with an internal cross-section of approximately 15 by 17 meters. The design flow of 8,000 cubic meters per second is approximately 3 times the discharge of the Rhine River at Cologne under normal conditions. This figure is derived from a mathematically calculated statistical projection. From the point of view of statistical probability, a peak flow of this magnitude will only occur once in a millennium. Normally, the path taken by the water out of the reservoir is through the powerhouse turbines. The power production structures are situated on the opposite slope of the valley to the spillway. The water flows through the screen and into the intake tower. Here it enters the steel-lined penstock, through which it is conducted under the dam and into the powerhouse. The penstock is approximately 250 meters long and has an internal diameter of 6.2 meters. Under full load conditions, which is a head of 84 meters and a flow volume of 185 cubic meters per second, the two Francis turbines in the powerhouse have a combined output of 2 times 69 megawatts. In general, whenever water power plants of the Randenigala type are constructed, the powerhouse has the longest construction time of any of the structures involved. For this reason, construction work on the powerhouse began as soon as possible, that is to say, well before the first steps were taken to divert the Mahaweli. After completion of the powerhouse pit, work began on the penstock, which was driven from here in an upstream direction. The drilling jumbo, which had been used to drive the two diversion tunnels, was also employed for the driving of the penstock. As the penstock cross-section was smaller, the entire tunnel could be driven in a full-face operation, which is without driving separate top, side and bottom benches. Parallel to the driving of the penstock, concreting work also commenced on the powerhouse. Here we can see the lowest point of construction, 13 meters below the water level of the Mahaweli, which flows past and directly adjacent to the powerhouse. Water inflows were constantly pumped off, however, and posed no problem. This carcass opening will subsequently house one of the two turbine units. 1 year later, the formwork and false work of the huge reinforced concrete beams are executed at the powerhouse construction site. This false work has been transported from beam to beam on the previously mounted powerhouse crane rails. Whilst the reinforced concrete construction work is proceeding at the powerhouse, the penstock has already been driven to the point where it opens out into what will later be the reservoir. From here, the huge steel pipes used to line the tunnel are now lowered into it for final assembly. The area around the welding seams of the steel pipes is preheated. After the pipe joints had been welded, the annular space between the steel lining and the tunnel wall was filled with concrete. A special fluid concrete was used here in order to guarantee that this intermediate space was filled in completely. Immediately after the last pipe had been lowered into the penstock, construction began on the intake tower. Its final height is 62 meters, but when the reservoir is completely filled, only 7 meters can be seen above the surface of the water. The intake tower houses the screening element and a steel gate which can be closed if necessary in order to cut off the flow of water from the reservoir. 2 years after commencement of work on the powerhouse, the first major component of the powerhouse equipment, the travelling crane for the turbine hall, was assembled. To do so, the erection crane had to lift and move the various components to their final position through the roof, which had been left open in this area. Building and steel construction operations had been suitably planned and coordinated well in advance in order to ensure that their convergence at this stage would not present any problems. Six months after the travelling crane in the turbine hall had been put into operation, the impeller of the first turbine outfit was lowered into its final position and installed in accordance with the joint schedule of the RCC and the powerhouse equipment suppliers. Only 3 months later, work commenced on the assembling of the generator. The stator blades are being inserted here. Whilst the equipment and interior work were proceeding at a brisk pace inside the powerhouse, work was also in full swing outside, where the outdoor switchyard was being assembled. The Federal Republic of Germany, through the Kreditanstalt für Wiederaufbau, has granted a soft loan to the value of 400 million D-marks for the Randenigala project. This project will benefit Sri Lanka in many ways. First of all, approximately 12% of Sri Lanka's electricity requirements will be met by the power plant. The very latest switching and control equipment has been installed in this plant. Furthermore, the annual floods, which have hitherto caused much devastation in downstream areas, will no longer occur. Finally, vast tracts of land, more than 20,000 hectares, will be irrigated and made arable by the Randenigala reservoir. Many thousands of families will thus be given the opportunity to earn a proper living. So Sri Lanka will be able to grow the basic foodstuffs needed for its expanding population. The Randenigala project, which meets the highest technical standards, is in harmony with its grandiose natural setting. The process of adaptation to the new lake by the environment has already commenced. A process which was made possible by the taming of the untamed Mahaweli.